So let's imagine to take the non-dimensional Navier-Stokes equation. Alright, so we have that something is incompressible. So we have the divergence of our velocity field, du, j, j, or just nabla, del, whatever you want to call it, equals to 0. And then we take the momentum equation where we have dui dt plus u j dui over dx j to be equals to negative 1 over rho then dp over dx I plus 1 over the Reynolds number d squared ui over dxj dxi. Okay, so this value here, when the Reynolds number approaches infinity, this entire thing becomes 0 because this thing here ends up being 0. So could we drop it from our equation? Well, before we do it, I want to point out one thing. This value here is a second order derivative because it's a Laplacian of our velocity vector. Oops, or just Laplacian of velocity. So if you imagine we have a constant I'm gonna call C times y double dot plus y dot plus y to be equals to just say even 0, can we drop these terms? This term if C is too small? Well, yes and no. We can drop it, but then we have to forego one of our boundary conditions. So which one are we dropping? Well, let's take an example and understand and derive which one we're dropping. So we are a velocity hitting a boundary condition. We're in a solid, so it's gonna go around this way, and let me make a better shape actually. Okay, so over here we're gonna have vorticity because of the non-slip condition. However, the incoming flow is irrotational. So the only way that this vorticity is created is by the non-slip condition. And we know that the viscosity um, has as a consequence, so the viscosity of a fluid tends to spread, diffuse the vorticity. Let me just do vorticity vector away from surface. So it's gonna start from enough one. So it's gonna start from near the surface right here, and then it's gonna start increasing as time passes by, or of course as the fluid passes by. The vorticity at a certain time will be equal to a certain point over time will just be the derivative of vorticity at one point will be equal to 0. But the if we were to derive our vorticity vector actually, a tensor, or xi, it would not be equal to 0 if our viscosity isn't 0. So if we're taking the Reynolds number to be very high, so approaching infinity, what does it mean for our viscosity? Well, it means that it's equals to 0. So if it's equals to 0, it means that there's no diffusion. We do it in red because it's big. So we can say it's no diffusion of our vorticity. It means that the vorticity remains confined to the surface and it's infinitesimally like we have it's the layer that is going to create is going to be infinitesimally small. We can imagine that it pretty much has no idea. So another way of thinking of this is like a free stream. We can imagine that the free stream says that the flow at a certain distance far away from the object has no idea that the object even exists, and so we can imagine that happens to everything except of course right at the surface. So we now have we are dropping the no-slip condition because we can imagine that our fluid is slipping, and so instead of having a velocity profile to be like this, we're going to have a velocity profile to be there's in color like this. It's tangent to our surface. In fact, it is the full tangency condition as the Reynolds number increases. Increases. Yeah. So if there's no viscosity, or um, we have no vorticity, and we can therefore that our vorticity vector is going to be equal to zero, or the curl of our velocity field is going to be equal to zero. And what does this mean? Well, a rule tells us that the curl of the gradient of a potential field is always equal to zero. So we can say that U is now equals to a gradient field, the gradient of a velocity potential. So we can call this velocity potential. Okay. So now we derive that we have a velocity potential here, and if we take and since we said that our fluid is now compressible, so divergence equals zero, we take the divergence of a gradient and we say equals to zero, we have the Laplacian to be equals to the Laplacian of a potential field is equals to zero. The Laplacian is also linear. Well, Laplacian actually allows superposition. So our potential field it can be the summation or the scalar of two fields. Um, and now we know that well, we dropped our no-slip boundary condition. So what are the boundary conditions that we have? We have free stream, um, and we have that at solid surfaces, the force, well, actually, sorry, the gradient of our velocity field is perpendicular to our surface equals to zero because it just tangent this. Okay? Uh, and in an incompressible, inviscid rotational flow, the total pressure will be constant, so we can use Bernoulli's equation. Bernoulli. And we can say the pressure plus 1/2 of density times what would be our velocity squared, which in our case we can just say it's equals to our gradient of a field dotted with the gradient of a field, same field, is equals to the our non-parameterized pressure plus 1/2 the density times our velocity non-parameterized squared, because of course this end up giving us our velocity squared. This works in all coordinate systems, so it can also work in the um, sorry, it can also work in uh, um, cylindrical and polar. And one thing I'll say last is the stream function we said was equals to our u dy and our v dx are negative. So those are one and two, of course, two components. Um, the gradient, though, of a field will give us something that is perpendicular to the field. So this part here will be perpendicular to our full field, to our velocity potential. So it means that our stream function is perpendicular to our velocity potential, orthogonal. The velocity of the velocity potential is orthogonal to the stream function.